Welcome to the course! You've begun one of the most complete overviews on data science tooling that you'll currently find on the internet. This doesn't mean that we cover each and every tool, but later in the course we'll introduce a comprehensive list of tasks a data scientist needs to perform, and give you the top 2 or 3 open source and commercial tools available to complete them. We also explain how the tools overlap in functionality, what their pros and cons are, and how these tools can address the whole data science pipeline. Let's start with data. Data is obviously central to data scientists. In this course, we'll show you how to manage, extract, transform, analyze, and visualize data. Now, you might be able to survive data science without programming skills if you use the right set of tools. However, we highly recommend getting familiar with programming and the related programming frameworks for data science. To help you along, we'll introduce you to the most commonly used programming languages and frameworks available for data science. That said, there is a lot of automation available in the latest tooling that a data scientist can use. In this course, we'll explain how to make use of those tools to save time and uncover inspiration. Visual programming is available in many tools. In this course, you'll learn how visual programming can be used to speed up development time and to help non-programmers enter the field of data science. Open source software is leading the field of data science, but its total costs of ownership, or TCO, can be higher at times due to configuration, customization, and maintenance costs. As a result, commercial software also has its place, especially since the new generation of commercial data science software leverages open source software and open standards. This makes it easy to migrate between tools and can reduce overall TCO. In this course, we'll introduce you to both open source and commercial software and point out their strengths and weaknesses for data science. We'll also show you ways that you can take advantage of their respective strengths. Finally, we'll show you how cloud computing can be used to further speed up and facilitate data scientists' work. We'll introduce you to the most commonly used and newly emerging cloud tools for data science. In addition to lectures, this course has numerous labs to make you more familiar with the material and get hands-on experience. There are also multiple quizzes to test your learning. There's nothing left but to begin. We're very happy to have you with us as you start your data science journey. If you have any trouble with any of the course material, please don't hesitate to contact us in the discussion forum. Let's get started. The languages of data science. For anyone just getting started on their data science journey, the range of technical options can be overwhelming. There is a dizzying amount of choices when it comes to programming languages. Each has its own strengths and weaknesses, and there is no one right answer to the question of which one you should learn first. The answer to that question depends largely on your needs, the problems you are trying to solve, and who you are solving them for. Python, R, and SQL are the languages that we recommend you consider first and foremost, but there are so many others that have their own strengths and features. Scala, Java, C++, and Julia are some of the most popular. JavaScript, PHP, Go, Ruby, and Visual Basic all have their own unique use cases as well. The language you choose to learn will depend on the things you need to accomplish and the problems you need to solve. It will also depend on what company you work for, what role you have, and the age of your existing application. We'll explore the answers to this question as we dive into the popular languages in the data science industry. There are many roles available for people who are interested in getting involved in data science. Business analyst, database engineer, data analyst, data engineer, data scientist, research scientist, software engineer, statistician, product manager, project manager, etc. Let's dive into what we will learn in Lesson 1. We will put most of our focus on the top 3 data science languages, Python, R, and SQL, which each have their own lessons. Then, we will go on to highlight other noteworthy languages and what makes them special. Then, we'll finish with a short quiz to test your knowledge. Here's what we'll cover: Python, R, SQL, other noteworthy data science languages, practice quiz. In this video, we will review the high-level features of the Python programming language. Python is a powerhouse language. It is by far the most popular programming language for data science. According to the 2019 Kaggle Data Science and Machine Learning Survey, 75% of the over 10,000 respondents from around the world reported that they use Python on a regular basis. Glassdoor reported that in 2019, more than 75% of data science positions listed included Python in their job descriptions. When asked which language an aspiring data scientist should learn first, most data scientists say Python. You're probably thinking, why on earth is Python so popular? Well, let's start with the people who use Python. If you already know how to program, then Python is great for you because it uses clear, readable syntax. You can do many of the things you are used to doing in other programming languages, but with Python, you can do it with less code. If you want to learn to program, it's also a great starter language because of the huge global community and wealth of documentation. In fact, several different surveys in 2019 found that over 80% of data professionals worldwide use Python. Python is useful for many situations, including data science, AI and machine learning, web development, and IoT devices like the Raspberry Pi. Large organizations that use Python heavily include IBM, Wikipedia, Google, Yahoo, CERN, NASA, Facebook, Amazon, Instagram, Spotify, and Reddit. Python is a powerful general-purpose programming language that can do a lot of things. It is widely supported by a global community and shepherded by the Python Software Foundation. Python is a high-level, general-purpose programming language that can be applied to many different classes of problems. It has a large standard library that provides tools suited to many different tasks, including but not limited to databases, automation, web scraping, text processing, image processing, machine learning, and data analytics. For data science, you can use Python's scientific computing libraries such as Pandas, NumPy, SciPy, and Matplotlib. For artificial intelligence, it has TensorFlow, PyTorch, Keras, and scikit-learn. Python can also be used for natural language processing, NLP, using the Natural Language Toolkit, NLTK. Another great selling point is the Python community, which has a well-documented history of paving the way for diversity and inclusion efforts in the tech industry as a whole. The Python language has a code of conduct executed by the Python Software Foundation that seeks to ensure safety and inclusion for all in both online and in-person Python communities. There are also communities like PyLadies that seek to create spaces for people interested in Python to learn in safe and inclusive environments. PyLadies is an international mentorship group with a focus on helping more women become active participants and leaders in the Python open source community. In this video, we will give a brief overview of the R programming language. After our last video on Python, where we discussed its wide adoption, you might be wondering why on earth you should consider learning any other language. Well, according to the results of the 2019 Kaggle Data Science Survey, which had over 10,000 respondents from around the world, learning up to 3 languages can increase your salary, and R has a lot to offer you. Like Python, R is free to use, but it's a new project. Instead of being open source, it's actually free software. So, if Python is open source and R is free software, what's the difference? Well, both open source and free software commonly refer to the same set of licenses. Many open source projects use the GNU General Public License, for example. Both open source and free software support collaboration. In many cases, but not all, these terms can be used interchangeably. The Open Source Initiative, OSI, champions open source, while the Free Software Foundation, FSF, defines free software. Open source is more business-focused, while free software is more focused on a set of values. Back to why you should learn R. Because it's a free software project, you can use the language in the same way that you contribute to open source, and it allows for public collaboration and private and commercial use. Plus, R is another language supported by a wide global community of people passionate about making it possible to use the language to solve big problems. Who is R for? It's most often used by statisticians, mathematicians, and data miners for developing statistical software, graphing, and data analysis. The language's array-oriented syntax makes it easier to translate from math to code, especially for someone with no or minimal programming background. According to Kaggle's Data Science and Machine Learning Survey, most folks learn R when they're a few years into their data science career, but it remains a welcoming language to those who don't have a software programming background. R is popular in academia, but companies that use R include IBM, Google, Facebook, Microsoft, Bank of America, Ford, TechCrunch, Uber, and Trulia. R has become the world's largest repository of statistical knowledge. As of 2018, R has more than 15,000 publicly released packages, making it possible to conduct complex exploratory data analysis. R integrates well with other computer languages, such as C++, Java, C, .NET, and Python. Common mathematical operations, such as matrix multiplication, work straight out of the box. R has stronger object-oriented programming facilities than most statistical computing languages. There are many ways to connect with other R users around the globe. Communities such as User, YR, Saturdays, and R Ladies are all great to connect with. And you can also check out the R Project website for R conferences and events. In this video, we'll take a high-level look at SQL. SQL is a bit different from other languages we've covered so far. First off, it's formally pronounced SQL, although some people say SQL. While the acronym stands for Structured Query Language, many people do not consider SQL to be like other software development languages because it's a non-procedural language and its scope is limited to querying and managing data. While it is not a data science language per se, data scientists regularly use it because it's simple and powerful. Another couple of neat facts about SQL. It's much older than Python and R by about 20 years, having first appeared in 1974, and SQL was developed at IBM. This language is useful in handling structured data, that is, the data incorporating relations among entities and variables. SQL was designed for managing data in relational databases. Here you see a diagram showing the general structure of a relational database. A relational database is formed by collections of two-dimensional tables, for example, datasets and Microsoft Excel spreadsheets. Each of these tables is then formed by a fixed number of columns and any number of rows. But even though SQL was originally developed for use with relational databases, because it's so pervasive and easy to use, SQL interfaces for many NoSQL and big data repositories have also been developed. The SQL language is subdivided into several language elements, including clauses, expressions, predicates, queries, and statements. So what makes SQL great? Knowing SQL will help you do many different jobs in data science, including business and data analyst, and it's a must in data engineering. When performing operations with SQL, you access the data directly. There's no need to copy it beforehand. This can speed up workflow executions considerably. SQL is the interpreter between you and the database. SQL is an American National Standards Institute, or ANSI, standard, which means if you learn SQL and use it with one database, you will be able to easily apply that SQL knowledge to many other databases. There are many different SQL databases available, including MySQL, IMDB2, PostgreSQL, Apache OpenOffice Base, SQLite, Oracle, MariaDB, Microsoft SQL Server, and more. The syntax for the SQL you write might change a little bit based on the relational database management system you're using. If you're looking to learn SQL, you might be best served to focus on a specific relational database and then plug into the community for that specific platform. There are many great introductory courses on SQL available. So far, we've reviewed Python, R, and SQL. In this video, we will review some other languages that have compelling use cases for data science. Okay, so indisputably, Python, R, and SQL are the three most popular languages that data scientists use. But there are many other languages that are worth your time when considering which language to use to solve a particular data science problem. Scala, Java, C++, and Julia are probably the most traditional data science languages on this slide. But JavaScript, PHP, Go, Ruby, Visual Basic, and others have all found their place in the data science community as well. I won't dive as deeply into each of these languages, but I'll mention some notable highlights. Java is a tried-and-true general-purpose, object-oriented programming language. It's been widely adopted in the enterprise space and is designed to be fast and scalable. Java applications are compiled to bytecode and run on the Java Virtual Machine, or JVM. Some notable data science tools built with Java include Weka for data mining, Java ML, which is a machine learning library, Apache ML-lib, which makes machine learning scalable, and Deep Learning 4J for deep learning. Apache Hadoop is another Java-built application. It manages data processing and storage for big data applications running in clustered systems. Scala is a general-purpose programming language that provides support for functional programming and a strong static type system. Many of the design decisions in the construction of the Scala language were made to address criticisms of Java. Scala is also interoperable with Java, as it runs on the JVM. The name Scala is a combination of scalable and language. This language is designed to grow along with the demands of its users. For data science, the most popular program built using Scala is Apache Spark. Spark is a fast and general-purpose cluster computing system. It provides APIs that make parallel jobs easy to write, and an optimized engine that supports general computation graphs. Spark includes Shark, which is a query engine, ML-lib for machine learning, GraphX for graph processing, and Spark Streaming. Apache Spark was designed to be faster than Hadoop. C++ is a general-purpose programming language. It is an extension of the C programming language, or C with classes. C++ improves processing speed, enables system programming, and provides broader control over the software application. Many organizations that use Python or other high-level languages for data analysis and exploratory tasks still rely on C++ to develop programs that feed that data to customers in real time. For data science, a popular deep learning library for data flow called TensorFlow was built with C++. But while C++ is the foundation of TensorFlow, it runs on a Python interface, so you don't need to know C++ to use it. MongoDB, a NoSQL database for big data management, was built with C++. Caffe is a deep learning algorithm repository built with C++ with Python and MATLAB bindings. A core technology for the World Wide Web, JavaScript, is a general-purpose language that extended beyond the browser with the creation of Node.js and other server-side approaches. JavaScript is not related to Java language. For data science, the most popular implementation is undoubtedly TensorFlow.js. TensorFlow.js makes machine learning and deep learning possible in Node.js as well as in the browser. TensorFlow.js was also adopted by other open-source libraries, including Brain.js and MachineLearn.js. The R.js project is another great implementation of JavaScript for data science. R.js has rewritten linear algebra specifications from the R language into TypeScript. This rewrite will provide a foundation for other projects to implement more powerful math-based frameworks like NumPy and SciPy of Python. TypeScript is a superset of JavaScript. Julia was designed at MIT for high-performance numerical analysis and computational science. It provides speedy development like Python or R while producing programs that run as fast as C or Fortran programs. Julia is compiled, which means that the code is executed directly on the processor as executable code. It calls C, Go, Java, MATLAB, R, Fortran, and Python libraries, and has refined parallelism. The Julia language is relatively new, having been written in 2012, but it has a lot of promise for future impact on the data science industry. JuliaDB is a particularly useful application of Julia for data science. It's a package for working with large persistent data sets. That's as far as we'll dig into the many languages that are used to solve data science problems. If you have experience with a particular language, I recommend you do a web search to see what might already be possible in terms of using it for data science. You might be surprised at the possibilities. Open source tools are available for various data science tasks. In this video, we'll have a look at the different data science tasks. In subsequent videos, we'll walk through the most commonly used open source tools for those tasks. The most important tools are covered throughout this course. Data management is the process of persisting and retrieving data. Data integration and transformation, often referred to as extract, transform, and load, or ETL, is the process of retrieving data from remote data management systems. Transforming data and loading it into a local data management system is also part of data integration and transformation. Data visualization is part of an initial data exploration process, as well as being part of a final deliverable. Model building is the process of creating a machine learning or deep learning model using an appropriate algorithm with a lot of data. Model deployment makes such a machine learning or deep learning model available to third-party applications. Model monitoring and assessment ensures continuous performance quality checks on the deployed models. These checks are for accuracy, fairness, and adversarial robustness. Code asset management uses versioning and other collaborative features to facilitate teamwork. Data asset management also supports replication, backup, and access rights management. Development environments, commonly known as integrated development environments or IDEs, are tools that help the data scientists to implement, execute, test, and deploy their work. Execution environments are tools where data processing, model training, and deployment take place. Finally, there is fully integrated visual tooling available that covers all the previous tooling components, either partially or completely. This concludes this video. In the next video, we'll start looking at open source tools for data science tasks. In part 1 of this two-part series, we'll cover data management, open source data integration, transformation, and visualization tools. The most widely used open source data management tools are relational databases, such as MySQL and PostgreSQL, NoSQL databases such as MongoDB, Apache CouchDB, and Apache Cassandra, and file-based tools such as the Hadoop file system or cloud file systems like Ceph. Finally, Elasticsearch is mainly used for storing text data and creating a search index for fast document retrieval. The task of data integration and transformation in the classic data warehousing world is called ETL, which stands for Extract, Transform, and Load. These days, data scientists often propose the term ELT, Extract, Load, Transform, stressing the fact that data is dumped somewhere and the data engineer or data scientist themselves is responsible for data. Another term for this process has now emerged: data refining and cleaning. Here are the most widely used open source data integration and transformation tools. Apache Airflow, originally created by Airbnb. Kubeflow, which enables you to execute data science pipelines on top of Kubernetes. Apache Kafka, which originated from LinkedIn. Apache NiFi, which delivers a very nice visual editor. Apache Spark SQL, which enables you to use ANSI SQL and scales up to compute clusters of thousands of nodes. And Node-RED, which also provides a visual editor. Node-RED consumes so little in resources that it even runs on small devices like a Raspberry Pi. We'll now introduce the most widely used open source data visualization tools. We have to distinguish between programming libraries where you need to use code and tools that contain a user interface. The most popular libraries are covered in the next videos. A similar approach uses Hue, which can create visualizations from SQL queries. Kibana, a data exploration and visualization web application, is limited to Elasticsearch, the data provider. Finally, Apache Superset is a data exploration and visualization web application. Model deployment is extremely important. Once you've created a machine learning model capable of predicting some key aspects of the future, you should make that model consumable by other developers and turn it into an API. Apache Prediction I/O currently only supports Apache Spark ML models for deployment, but support for all sorts of other libraries is on the roadmap. Seldon is an interesting product since it supports nearly every framework, including TensorFlow, Apache Spark ML, R, and scikit-learn. Seldon can run on top of Kubernetes and Red Hat OpenShift. Another way to deploy Spark ML models is using mLeap. Finally, TensorFlow can serve any of its models using the TensorFlow service. You can deploy to an embedded device like a Raspberry Pi or a smartphone using TensorFlow Lite, and even deploy to a web browser using TensorFlow.js. Model monitoring is another crucial step. Once you've deployed a machine learning model, you need to keep track of its prediction performance as new data arrives in order to maintain outdated models. Following are some examples of model monitoring tools. ModelDB is a machine model metadatabase where information about the models are stored and can be queried. It natively supports Apache Spark ML pipelines and scikit-learn. A generic multipurpose tool called Prometheus is also widely used for machine learning model monitoring, although it's not specifically made for this purpose. Model performance is not exclusively measured through accuracy. Model bias against protected groups like gender or race is also important. The IBM AI Fairness 360 open source toolkit does exactly this. It detects and mitigates against bias in machine learning models. Machine learning models, especially neural network-based deep learning models, can be subject to adversarial attacks, where an attacker tries to fool the model with manipulated data or by manipulating the model itself. The IBM Adversarial Robustness 360 toolbox can be used to detect vulnerability to adversarial attacks and help make the model more robust. Machine learning models, often considered to be a black box that applies some mysterious magic. The IBM AI Explainability 360 toolkit makes the machine learning process more understandable by finding similar examples within a dataset that can be presented to a user for manual comparison. The IBM AI Explainability 360 toolkit can also illustrate training for a simpler machine learning model by explaining how different input variables affect the final decision of the model. Options for code asset management tools have been greatly simplified. For code asset management, also referred to as version management or version control, Git is now the standard. Multiple services have emerged to support Git, with the most prominent being GitHub, which provides hosting for software development version management. The runner-up is definitely GitLab, which has the advantage of being a fully open source platform that you can host and manage yourself. Another choice is Bitbucket. Data asset management, also known as data governance or data lineage, is another crucial part of enterprise-grade data science. Data has to be versioned and annotated with metadata. Apache Atlas is a tool that supports this task. Another interesting project, ODPI Egeria, is managed through the Linux Foundation and is an open ecosystem. It offers a set of open APIs, types, and interchange protocols that metadata repositories use to share and exchange data. Finally, Kylo is an open-source data lake management software platform that provides extensive support for a wide range of data asset management tasks. This concludes part 1 of this 2-part series. Let's move on to part 2. Welcome to part 2 of this series. In this section, we'll cover the development environment, open source data integration, transformation, and visualization tools. One of the most popular current development environments that data scientists are using is Jupyter. Jupyter first emerged as a tool for interactive Python programming. It now supports more than 100 different programming languages through kernels. Kernels shouldn't be confused with operating system kernels. Jupyter kernels are encapsulating the different interactive interpreters for the different programming languages. A key property of Jupyter notebooks is the ability to unify documentation, code, output from the code, shell commands, and visualizations into a single document. Jupyter Lab is the next generation of Jupyter notebooks, and in the long term will actually replace Jupyter notebooks. The architectural changes being introduced in Jupyter Lab makes Jupyter more modern and modular. From a user's perspective, the main difference introduced by Jupyter Lab is the ability to open different types of files, including Jupyter notebooks, data, and terminals. You can then arrange these files on the canvas. Although Apache Zeppelin has been fully re-implemented, it's inspired by Jupyter notebooks and provides a similar experience. One key differentiator is the integrated plotting capability. In Jupyter notebooks, you are required to use external libraries. In Apache Zeppelin, plotting doesn't require coding. You can also extend these capabilities by using additional libraries. RStudio is one of the oldest development environments for statistics and data science, having been introduced in 2011. It exclusively runs R and all associated R libraries. However, Python development is possible, and R is therefore tightly integrated into this tool to provide an optimal user experience. RStudio unifies programming, execution, debugging, remote data access, data exploration, and visualization into a single tool. Spider tries to mimic the behavior of RStudio to bring its functionality to the Python world. Although Spider does not have the same level of functionality as RStudio, data scientists do consider it an alternative. But in the Python world, Jupyter is used more frequently. This diagram shows how Spider integrates code, documentation, visualizations, and other components into a single canvas. Sometimes your data doesn't fit into a single computer storage or main memory capacity. That's where cluster execution environments come in. The well-known cluster computing framework Apache Spark is among the most active Apache projects and is used across all industries, including many Fortune 500 companies. The key property of Apache Spark is linear scalability. This means if you double the number of servers in a cluster, you also roughly double its performance. After Apache Spark began to gain market share, Apache Flink was created. The key difference between Apache Spark and Apache Flink is that Apache Spark is a batch data processing engine, capable of processing huge amounts of data file by file. Apache Flink, on the other hand, is a stream processing image, with its main focus on processing real-time data streams. Although Engine supports both data processing paradigms, Apache Spark is usually the choice in most use cases. One of the latest developments in the data science execution environments is called Ray, which is a clear focus on large-scale deep learning model training. Let's look at open-source tools for data scientists that are fully integrated and visual. With these tools, no programming knowledge is necessary. Most important tasks are supported by these tools, with tasks including data integration, transformation, data visualization, and model building. KNIME originated at the University of Constance in 2004. As you can see, KNIME has a visual user interface with drag-and-drop capabilities. It also has built-in visualization capabilities. KNIME can be extended by programming in R and Python and has connectors to Apache Spark. Another example of this group of tools is Orange. It's less flexible than KNIME, but easier to use. In this section, you've learned about the most common data science tasks and which open-source tools are relevant to those tasks. In the next video, we'll describe some established commercial tools that you'll encounter in your data science experience. Let's move on to the next video to get more details. We previously covered open-source tools for data science. Now let's look at the commercial options you'll find in many enterprise projects. Let's revisit our overview of different tool categories. In data management, most of an enterprise's relevant data is stored in an Oracle database, Microsoft SQL Server, or IBM DB2. Although open-source databases are gaining popularity, those three data management products are still considered the industry standard. They won't disappear in the near future. It's not just about functionality. Data is at the heart of every organization, and the availability of commercial supports plays a major role. Commercial supports are delivered directly from software vendors, influential partners, and support networks. When we focus on commercial data integration tools, we're talking about extract, transform, and load, or ETL tools. According to Gartner Magic Quadrant, Informatica PowerCenter and IBM InfoSphere DataStage are the leaders, followed by products from SAP, Oracle, SAS, Talend, and Microsoft. These tools support design and deployment of ETL data processing pipelines through a graphical interface. They also provide connectors to most of the commercial and open-source target information systems. Finally, Watson Studio Desktop includes a component called Data Refinery, which enables the defining and execution of data integration processes in a spreadsheet style. In the commercial environment, data visualizations are utilizing business intelligence or BI tools. Their main focus is to create visually attractive and easy-to-understand reports and live dashboards. The most prominent commercial examples are Tableau, Microsoft Power BI, and IBM Cognos Analytics. Another type of visualization targets data scientists rather than regular users. A sample problem might be, how can different columns in a table relate to each other? This type of functionality is contained in Watson Studio Desktop. If you want to build a machine learning model using a commercial tool, you should consider using a data mining product. The most prominent of these types of products are SPSS Modeler and SAS Enterprise Miner. In addition, a version of SPSS Modeler is also available in Watson Studio Desktop, based on the cloud version of the tool. We'll talk more about cloud-based tools in the next video. In commercial software, model deployment is tightly integrated in the model building process. This diagram shows an example of the SPSS collaboration and deployment services which are used to deploy any type of asset created by the SPSS software tools suite. Other vendors use the same type of process. Commercial software can also export models in an open format. For example, SPSS Modeler supports the exporting of models as Predictive Model Markup Language, or PMML, which can be read by many other commercial and open software packages. Model monitoring is a new discipline, and there are currently no relevant commercial tools available. As a result, open source is the first choice. The same is true for code asset management. Open source with Git and GitHub is the effective standard. Data asset management, also called data governance or data lineage, is a crucial part of enterprise-grade data science. Data must be versioned and annotated using metadata. Vendors, including Informatica Enterprise Data Governance and IBM, provide tools for these specific tasks. The IBM InfoSphere Information Governance Catalog covers functions like Data Dictionary, which facilitates discovery of data assets. Each data asset is assigned to a data steward, the data owner. The data owner is responsible for that data asset and can be contacted. Data lineage is also covered. This enables a user to track back through the transformation steps followed in creating the data assets. The data lineage also includes a reference to the actual source data. Rules and policies can be added to reflect complex regulatory and business requirements for data privacy and retention. Watson Studio is a fully integrated development environment for data scientists. It's usually consumed through the cloud, and we'll cover more about it in a later lesson. There is also a desktop version available. Watson Studio Desktop combines Jupyter notebooks with graphical tools to maximize data scientists' performance. Watson Studio, together with Watson OpenScale, is a fully integrated tool covering the full data science lifecycle and all the tasks we've discussed previously. We'll talk more about both in the next lesson, but just keep in mind that they can be deployed in a local data center on top of Kubernetes or Red Hat OpenShift. Another example of a fully integrated commercial tool is H2O Driverless AI, which covers the complete data science lifecycle. In this lesson, you've learned how most common data science tasks are supported by commercial tools. In the next video, we'll discover data science tools that are available exclusively on the cloud. Since we've previously covered open source tools for data science, let's look at the commercial options you'll find in many enterprise projects. Take another look at the overview of different tool categories. Since cloud products are a newer species, they follow the trend of having multiple tasks integrated into a single tool. This especially holds true for the tasks marked green in the diagram. Let's start with the fully integrated visual tools category. Since these tools introduce a component where large-scale execution of data science workflows happens in compute clusters, we've changed the title here and added the word platform. These clusters are composed of multiple server machines, transparently for the user in the background. Watson Studio, together with Watson OpenScale, covers the complete development lifecycle for all data science, machine learning, and AI tasks. Another example is Microsoft Azure Machine Learning. This is also a fully cloud-hosted offering supporting the complete development lifecycle of all data science, machine learning, and AI tasks. And finally, another example is H2O Driverless AI, which we've already introduced in the last video. Although it is a product that you download and install, one-click deployment is available for the common cloud service providers. Since operations and maintenance are not done by the cloud provider, as is the case with Watson Studio, OpenScale, and Azure Machine Learning, this delivery model should not be confused with platform or software as a service, PaaS or SaaS. In data management, with some exceptions, there are SaaS versions of existing open source and commercial tools. Remember, SaaS stands for Software as a Service. It means that the cloud provider operates the tool for you in the cloud. As an example, the cloud provider operates the product by backing up your data and configuration and installing updates. As mentioned, there is proprietary tooling, which is only available as a cloud product. Sometimes it's only available from a single cloud provider. One example of such a service is Amazon Web Services DynamoDB, a NoSQL database that allows storage and retrieval of data in a key value or a document store format. The most prominent document data structure is JSON. Another flavor of such a service is Cloudant, which is a database as a service offering, but under the hood it is based on the open source Apache CouchDB. It has an advantage. Although complex operational tasks like updating, backup, restore, and scaling are done by the cloud provider, under the hood, this offering is compatible with CouchDB. Therefore, the application can be migrated to another CouchDB server without changing the application. And IBM offers DB2 as a service as well. This is an example of a commercial database made available as a software as a service offering in the cloud, taking operational tasks away from the user. When it comes to commercial data integration tools, we talk not only about extract, transform, and load, or ETL tools, but also about extract, load, and transform, or ELT tools. This means the transformation steps are not done by a data integration team, but are pushed towards the domain of the data scientist or data engineer. Two widely used commercial data integration tools are Informatica Cloud Data Integration and IBM's Data Refinery. Data Refinery enables transformation of large amounts of raw data into consumable, quality information in a spreadsheet-like user interface. Data Refinery is part of IBM Watson Studio. The market for cloud data visualization tools is huge, and every major cloud vendor has one. An example of a smaller company's cloud-based data visualization tool is Datamere. IBM offers its famous Cognos Business Intelligence Suite as a cloud solution as well. IBM Data Refinery also offers data exploration and visualization functionality in Watson Studio. Again, these are just some examples of a rapidly changing and growing commercial ecosystem among a huge number of established and emerging vendors. In Watson Studio, an abundance of different visualizations can be used to better understand data. For example, this 3D bar chart enables you to visualize a target value on the vertical dimension, which is dependent on two other values on the horizontal dimensions. Coloring enables you to visualize a third dimension. Hierarchical change bundling enables you to visualize correlations and affiliations between entities. If sufficient, a classic bar chart can do the job as well, whereas a 2D scatter plot with a heat map shows two dependent data fields, one on the y-axis and one as color intensity. A tree map shows distribution of subsets within a set. The famous pie chart does the same but in a non-hierarchical manner. And finally, a word cloud pops out significant terms in a document corpus. Model building can be done using a service such as Watson Machine Learning. Watson Machine Learning can train and build models using various open source libraries. Google has a similar service on their cloud called AI Platform Training. Nearly every cloud provider has a solution for this task. Model deployment in commercial software is usually tightly integrated to the model building process. Here is an example of the SPSS collaboration and deployment services, which can be used to deploy any type of asset created by the SPSS software tools suite. The same holds for other vendors. In addition, commercial software can export models in an open format. As an example, SPSS Modeler supports exporting models as Predictive Model Markup Language, or PMML, which can be read by numerous other commercial and open software packages. Watson Machine Learning can also be used to deploy a model and make it available to consumers using a REST interface. Amazon SageMaker Model Monitor is an example of a cloud tool that continuously monitors deployed machine learning and deep learning models. Again, every major cloud provider has a similar tooling. This is also the case for Watson OpenScale. OpenScale and Watson Studio unify the landscape. Everything marked in green can be done using Watson Studio and Watson OpenScale. OpenScale will be covered in a later video. You've learned how the most common tasks in data science are supported by commercial cloud tools. Integration provides us the ability to use the same tools for multiple tasks. In the next videos, we'll look at packages, APIs, datasets, and models for data science. In this video, we will review several data science libraries. Libraries are a collection of functions and methods that enable you to perform a wide variety of actions without writing the code yourself. We will focus on Python libraries, scientific computing libraries in Python, visualization libraries in Python, high-level machine learning and deep learning libraries. High-level simply means you don't have to worry about details, although this makes it difficult to study or improve. Deep learning libraries in Python, libraries used in other languages. Libraries usually contain built-in modules providing different functionalities that you can use directly. These are sometimes called frameworks. There are also extensive libraries offering a broad range of facilities. Pandas offers data structures and tools for effective data cleaning, manipulation, and analysis. It provides tools to work with different types of data. The primary instrument of Pandas is a two-dimensional table consisting of columns and rows. This table is called a data frame and is designed to provide easy indexing so you can work with your data. NumPy libraries are based on arrays, enabling you to apply mathematical functions to these arrays. Pandas is actually built on top of NumPy. Data visualization methods are a great way to communicate with others and show the meaningful results of analysis. These libraries enable you to create graphs, charts, and maps. The Matplotlib package is the most well-known library for data visualization, and it's excellent for making graphs and plots. The graphs are also highly customizable. Another high-level visualization library, Seaborn, is based on Matplotlib. Seaborn makes it easy to generate plots like heat maps, time series, and violin plots. For machine learning, the scikit-learn library contains tools for statistical modeling, including regression, classification, clustering, and others. It is built on NumPy, SciPy, and Matplotlib, and it's relatively simple to get started. For this high-level approach, you define the model and specify the parameter types you would like to use. For deep learning, Keras enables you to build the standard deep learning model. Like scikit-learn, the high-level interface enables you to build models quickly and simply. It can function using graphics processing units, or GPUs, but for many deep learning cases, a lower-level environment is required. TensorFlow is a low-level framework used in large-scale production of deep learning models. It's designed for production but can be unwieldy for experimentation. PyTorch is used for experimentation, making it simple for researchers to test their ideas. Apache Spark is a general-purpose cluster computing framework that enables you to process data using compute clusters. This means that you process data in parallel, using multiple computers simultaneously. The Spark library has similar functionality as Pandas, NumPy, and scikit-learn. Apache Spark data processing jobs can use Python, R, Scala, or SQL. There are many libraries for Scala, which is predominantly used in data engineering but is also sometimes used in data science. Let's discuss some of the libraries that are complementary to Spark. Vegas is a Scala library for statistical data visualizations. With Vegas, you can work with the data files as well as Spark data frames. For deep learning, you can use BigDL. R has built-in functionality for machine learning and data visualization, but there are also several complementary libraries. ggplot2 is a popular library for data visualization in R. You can also use libraries that enable you to interface with Keras and TensorFlow. R has been the de facto standard for open-source data science, but is now being superseded by Python. In this video, we will discuss Application Programming Interfaces, or APIs. Specifically, we will discuss what an API is, API libraries, REST APIs, including request and response. An API lets two pieces of software talk to each other. For example, you have your program, you have some data, you have other software components. You use the API to communicate with the other software components. You don't have to know how the API works, you just need to know its inputs and outputs. Remember, the API only refers to the interface or the part of the library that you see. The library refers to the whole thing. Consider the Pandas library. Pandas is actually a set of software components, many of which are not even written in Python. You have some data, you have a set of software components. We use the Pandas API to process the data by communicating with the other software components. There can be a single software component at the back end, but there can be a separate API for different languages. Consider TensorFlow written in C++. There are separate APIs in Python, JavaScript, C++, Java, and Go. The API is simply the interface. There are also multiple volunteer-developed APIs for TensorFlow. For example, Julia, MATLAB, R, Scala, and many more. REST APIs are another popular type of API. They enable you to communicate using the internet, taking advantage of storage, greater data access, artificial intelligence algorithms, and many other resources. The RE stands for representational, the S stands for state, the T stands for transfer. In REST APIs, your program is called the client. The API communicates with a web service that you call through the internet. A set of rules governs communication, input or request, and output or response. Here are some common API-related terms. You or your code can be thought of as a client. The web service is referred to as a resource. The client finds the service through an endpoint. The client sends the request to the resource and the response to the client. HTTP methods are a way of transmitting data over the internet. We tell the REST APIs what to do by sending a request. The request is usually communicated through an HTTP message. The HTTP message usually contains a JSON file, which contains instructions for the operation that we would like the service to perform. This operation is transmitted to the web service over the internet. The service performs the operation. Similarly, the web service returns a response through an HTTP message where the information is usually returned using a JSON file. This information is transmitted back to the client. The Watson Speech-to-Text API is an example of a REST API. This API converts speech to text. In the API call, you send a copy of the audio file to the API. This process is called a POST request. The API then sends the text transcription of what the individual is saying. The API is making a GET request. The Watson Language Translator API provides another example. You send the text you would like to translate into the API. The API translates the text and sends the translation back to you. In this case, we translate English to Spanish. In this video, we've discussed what an API is, API libraries, REST APIs, including request and response. Thank you for watching this video. In this video, we'll discuss datasets, what they are, why they are important in data science, and where to find them. Let's first loosely define what a dataset is. A dataset is a structured collection of data. Data embodies information that might be represented as text, numbers, or media such as images, audio, or video files. A dataset that is structured as tabular data comprises a collection of rows, which in turn comprise columns that store the information. One popular tabular data format is comma-separated values, or CSV. A CSV file is a delimited text file where each line represents a row, and data values are separated by a comma. For example, imagine a dataset of observations from a weather station. Each row represents an observation at a given time, while each column contains information about that particular observation, such as temperature, humidity, and other weather conditions. Hierarchical or network data structures are typically used to represent relationships between data. Hierarchical data is organized in a tree-like structure, whereas network data might be stored as a graph. For example, the connections between people on a social networking website are often represented in the form of a graph. A dataset might also include raw data files, such as images or audio. The MNIST dataset is popular for data science. It contains images of handwritten digits and is commonly used to train image processing systems. Traditionally, most datasets were considered to be private because they contain proprietary or confidential information, such as customer data, pricing data, or other commercially sensitive information. These datasets are typically not shared publicly. Over time, more and more public and private entities, such as scientific institutions, governments, organizations, and even companies have started to make datasets available to the public as open data, providing a wealth of information for free. For example, the United Nations and federal and municipal governments around the world have published many datasets on their websites, covering the economy, society, healthcare, transportation, environment, and much more. Access to these and other open datasets enable data scientists, researchers, analysts, and others to uncover previously unknown and potentially useful insights. They can create new applications for both commercial purposes and the public good. They can also carry out new research. Open data has played a significant role in the growth of data science, machine learning, and artificial intelligence, and has provided a way for practitioners to hone their skills on a wide variety of datasets. There are many open data sources on the Internet. You can find a comprehensive list of open data portals from around the world on the Open Knowledge Foundation's datacatalogs.org website. The United Nations, the European Union, and many other governmental and intergovernmental organizations maintain data repositories providing access to a wide range of information. On Kaggle, which is a popular data science online community, you can find and contribute data sets that might be of general interest. Last but not least, Google provides a search engine for data sets that might help you find the ones that have particular value for you. It's important to recognize that open data distribution and use might be restricted as defined by its licensing terms. In absence of a license for open data distribution, many datasets were shared in the past under open source software licenses. These licenses were not designed to cover the specific considerations related to the distribution and use of datasets. To address the issue, the Linux Foundation created the Community Data License Agreement, or CDLA. Two licenses were initially created for sharing data, CDLA Sharing and CDLA Permissive. The CDLA Sharing license grants you permission to use and modify the data. The license stipulates that if you publish your modified version of the data, you must do so under the same license terms as the original data. The CDLA Permissive license also grants you permission to use and modify the data. However, you are not required to share changes to the data. Note that neither license imposes any restrictions on results you might derive by using the data, which is important in data science. Let's say, for example, that you are building a model that performs a prediction. If you are training the model using CDLA licensed datasets, you are under no obligation to share the model, or to share it under a specific license if you do choose to share it. In this video, you've learned about open datasets, their role in data science, and where to find them. We've also introduced the Community Data License Agreement, which makes it easier to share open data. One important aspect that we didn't cover in this video is data quality and accuracy, which might vary greatly depending on who collected and contributed the dataset. While some open datasets might be good enough for personal use, they might not meet enterprise requirements due to the impact they might have on the business. In the next video, you will learn about the Data Asset Exchange, a curated open data repository. Despite the growth of open datasets that are available to the public, it can still be difficult to discover datasets that are both high quality and have clearly defined license and usage terms. To help solve this challenge, IBM created the Data Asset Exchange, or DAX, which we'll introduce in this video. DAX provides a trusted source for finding open datasets that are ready to use in enterprise applications. These datasets cover a wide variety of domains, including images, video, text, and audio. Because DAX provides a high level of curation for dataset quality, as well as licensing and usage terms, DAX datasets are typically easier to adopt, whether in research or commercial projects. Wherever possible, DAX aims to make datasets available under one of the variants of the Community Data License Agreement, in order to foster data sharing and collaboration. DAX also provides a single place to access unique datasets, in particular from IBM research projects. To make it easier for developers to get started with using the datasets, DAX also provides tutorials in the form of notebooks that walk through the basics of data cleaning, pre-processing, and exploratory analysis. For some datasets, there are also notebooks illustrating how to perform more complex analysis, such as creating charts, statistical analysis, time series analysis, training machine learning models, and integrating deep learning using the Model Asset Exchange, a project closely related to DAX and also available on the IBM developer website. In this way, DAX helps developers to create end-to-end analytic and machine learning workflows, and to consume open data and models with confidence under clearly defined license terms. Let's say you found a dataset that might be of interest to you. On the Dataset page, you can download the compressed dataset archive from cloud storage, explore the dataset using Jupyter Notebooks, review the dataset metadata, such as format, licensing terms, and size, and preview some parts of the dataset. Most datasets on DAX are complemented by one or more Jupyter Notebooks that you can use to perform data cleaning, pre-processing, and exploratory analysis. These notebooks run as is in Watson Studio, IBM's data science platform. Jupyter Notebooks and Watson Studio are covered later in this course. In this video, you've learned about IBM's Open Data Repository, the Data Asset Exchange. In the hands-on lab, you'll have a chance to explore the repository. In this video, we'll introduce you to machine learning and deep learning models. Data contains a wealth of information that can be used to solve certain types of problems. Traditional data analysis approaches, such as a person manually inspecting the data or a specialized computer program that automates the human analysis, quickly reach their limits due to the amount of data to be analyzed or the complexity of the problem. Machine learning uses algorithms, also known as models, to identify patterns in the data. The process by which the model learns these patterns from data is called model training. Once a model is trained, it can then be used to make predictions. When the model is presented with new data, it tries to make predictions or decisions based on the patterns it has learned from past data. Machine learning models can be divided into three basic classes: supervised learning, unsupervised learning, and reinforcement learning. Supervised learning is one of the most commonly used type of machine learning models. In supervised learning, a human provides input data and the correct outputs. The model tries to identify relationships and dependencies between the input data and the correct output. Generally speaking, supervised learning is used to solve regression and classification problems. Let's look at an example for each problem type. Regression models are used to predict a numeric or real value. For example, given information about past home sales, such as geographic location, size, number of bedrooms, and sales price, you can train a model to predict the estimated sales price for other homes with similar characteristics. Classification models are used to predict whether something belongs to a category or class. For example, given a set of emails along with a designation of whether or not they are considered spam, an algorithm can be trained to identify unsolicited emails. In unsupervised learning, the data is not labeled by a human. The models must analyze the data and try to identify patterns and structure within the data based only on the characteristics of the data itself. Clustering and anomaly detection are two examples of this learning style. Clustering models are used to divide each record of a dataset into one of a small number of similar groups. An example of a clustering model could be providing purchase recommendations for an e-commerce store based on past shopping behavior and the content of a shopping cart. Anomaly detection identifies outliers in a dataset, such as fraudulent credit card transactions or suspicious online login attempts. The third type of learning, reinforcement learning, is loosely based on the way human beings and other organisms learn. Think about a mouse in a maze. If the mouse gets to the end of the maze, it gets a piece of cheese. This is the reward for completing a task. The mouse learns through trial and error how to get through the maze to get as much cheese as it can. In a similar way, a reinforcement learning model learns the best set of actions to take, given its current environment, in order to get the most reward over time. This type of learning has recently been very successful in beating the best human players in games such as Go, chess, and popular strategy video games. Deep learning is a specialized type of machine learning. It refers to a general set of models and techniques that tries to loosely emulate the way the human brain solves a wide range of problems. It is commonly used to analyze natural language, both spoken and text, as well as images, audio, and video to forecast time series data and much more. Deep learning has had a lot of recent success in these and other areas, and is therefore becoming an increasingly popular and important tool for data science. Deep learning typically requires very large datasets of labeled data to train a model, is compute-intensive, and usually requires special-purpose hardware to achieve acceptable training times. You can build a custom deep learning model from scratch, or use pre-trained models from public model repositories. Deep learning models are implemented using popular frameworks such as TensorFlow, PyTorch, and Keras. Deep learning frameworks typically provide a Python API, and many support other programming languages such as C++ and JavaScript. You can download pre-trained, state-of-the-art models from repositories that are commonly referred to as model zoos. Popular model zoos include those provided by TensorFlow, PyTorch, Keras, and Onyx. Models are also published by academic and commercial research groups. While it is beyond the scope of this video to explain in detail how you would go about building a model, let's briefly outline the high-level tasks using an example. Assume you want to enable an application to identify objects and images by training a deep learning model. First, you collect and prepare data that will be used to train a model. Data preparation can be a time-consuming and labor-intensive process. In order to train a model to detect objects and images, you need to label the raw training data by, for example, drawing bounding boxes around objects and labeling them. Next, you build a model from scratch or select an existing model that might be well suited for the task from a public or private resource. You then train the model on your prepared data. During training, your model learns from the labeled data how to identify objects that are depicted in an image. Once training has commenced, you analyze the training results and repeat the process until the trained model performance meets your requirements. When the trained model performs as desired, you deploy it to make it available to your applications. In this video, you've learned about machine learning and deep learning, what they are used for, and where to find open-source models. In the next video, we'll introduce you to the Model Asset Exchange, a curated collection of ready-to-use and customizable deep learning models. In this video, we will introduce you to the Model Asset Exchange on IBM Developer, a free open-source resource for deep learning models. Throughout the video, we will refer to the Model Asset Exchange as MAX. In the previous video, we briefly outlined the high-level tasks you need to complete to train a model from scratch. Due to the amount of data, labor, time, and resources required to complete the tasks, time to value can be quite long. To reduce time to value, consider taking advantage of pre-trained models for certain types of problems. These pre-trained models can be ready to use right away, or they may take less time to train. The Model Asset Exchange is a free open-source repository for ready-to-use and customizable deep learning microservices. These microservices are configured to use pre-trained or custom trainable state-of-the-art deep learning models to solve custom business problems. These models have been reviewed, tested, and can be quickly deployed in local and cloud environments. All models in MAX are available under permissive open source licenses, making it easier to use them for personal and commercial purposes and reducing the risk of legal liabilities. On MAX, you can find models for a variety of domains, including image, audio, video, and natural language analysis. This list includes a small selection. In the lab for this module, you'll have a chance to explore those models. Let's take a look at the components of a typical model-serving microservice. Each microservice includes the following components: a pre-trained deep learning model, code that pre-processes the input before it is analyzed by the model, and code that post-processes the model output, a standardized public API that makes the service's functionality available to applications. The Max model serving microservices are built and distributed as open-source Docker images. Docker is a container platform that makes it easy to build applications and deploy them in a development, test, or production environment. The Docker image source is published on GitHub and can be downloaded, customized as needed, and used in personal or commercial environments. You can deploy and run these images in a test or production environment using Kubernetes, an open-source system for automating deployment, scaling, and management of containerized applications in private, hybrid, or public clouds. A popular enterprise-grade Kubernetes platform is Red Hat OpenShift, which is available on IBM Cloud, Google Cloud Platform, Amazon Web Services, and Microsoft Azure. The model-serving microservices expose a REST API that developers can use to incorporate deep learning into their applications and services. Because REST APIs can be consumed using any programming language, you can easily integrate these services into your existing ecosystem. The API exposes a prediction endpoint and one or more metadata endpoints. This example shows the endpoints for the object detection microservice. The /model/predict endpoint takes an image as input and returns as a response a list of objects that were detected in the image, along with the bounding box coordinates that identify where the detected object is located. Some prediction endpoints can also accept additional input parameters that impact the produced results, such as filters. This microservice exposes two metadata endpoints, /model/labels and /model/metadata. These endpoints provide information such as the objects that can be detected and the deep learning model used to derive the answer given the input. In the lab portion of this module, you will have a chance to explore and test these endpoints using a web browser. Each endpoint accepts application-friendly inputs, such as an image in JPEG, PNG, or GIF format, instead of a model-specific data structure. Each endpoint also generates application-friendly outputs, such as standardized JSON, which is a lightweight data interchange format. Let's take a closer look at what happens when an application invokes the prediction endpoint. In this example, a user has selected an image in a web application. The prediction endpoint is invoked, and the image is uploaded. The microservice prepares the input image for processing, runs the deep learning model that identifies objects in the image, generates a response using the prediction results, and returns the result to the application. The application renders the results by drawing bounding boxes and labels. In this video, we've introduced the Model Asset Exchange, a free and open-source repository for microservices that make deep learning functionality available to applications and services in local and cloud environments. In the lab, you will have a chance to try a model-serving microservice, explore its API, and learn more about how you can leverage it from a web application and an Internet of Things application. Welcome to Introduction to Jupyter Notebooks. This tutorial walks you through what Jupyter is and some basic syntax. The following videos will contain tutorials and hands-on practice. A Jupyter Notebook is a browser-based application that allows you to create and share documents that contain code, equations, visualizations, narrative text links, and so much more. It can be likened to a scientist's lab notebook where a scientist records all steps to perform their experiments and records the results so that it can be reproduced in the future. Similarly, a Jupyter Notebook allows a data scientist to record their data experiments, their results, and allows for the same experiment to be used and repeated by anyone. A Jupyter Notebook file allows data scientists to combine descriptive text, code blocks, and code output in a single file. When you run the code, it generates the outputs, including plots and tables, within the notebook file. And you can then export the notebook to a PDF or HTML file that can be then shared with anyone. Jupyter Notebooks originated as IPython, originally developed for the Python programming language. As it came to support additional languages, it was renamed Jupyter, which stands for Julia, Python, R. But nowadays, the notebook supports many other languages as well. Jupyter Lab is a browser-based application that allows you to access multiple Jupyter Notebook files as well as other code and data files. Jupyter Lab extends the functionalities of Jupyter Notebooks by enabling you to work with multiple notebooks, text editors, terminals, and custom components in a flexible, integrated, and extensible manner. Jupyter Lab allows for interactive control of the notebook cells and output, real-time editing markdowns, CSV, etc. It is compatible with several file formats like CSV, JSON, PDF, Vega, and more. And it is open source. Jupyter Notebooks can be used with a cloud-based service like IBM and Google Colab. They do not require you to install anything on your local machine. They give you access to the Jupyter Notebook environment. They do allow you to import and export notebooks using the standard IPython notebook file format, and they support the Python language and other languages as well. Jupyter Notebooks can be installed via the command line using the pip install function. Jupyter Notebooks can also be downloaded locally to your laptop through the Anaconda platform from anaconda.com. Anaconda is one of the popular distributions which includes Jupyter and Jupyter Lab. For the purposes of learning in this course, you have access to a hosted version of Jupyter Labs in Skills Network Labs, so you do not have to download and install anything on your own device in order to complete the hands-on labs. You will see a screen like this that launches the Jupyter Lab in the virtual environment. Simply click on Open Tool. You should now be familiar with how Jupyter Notebooks are used in data science for recording experiments and projects, how Jupyter Lab is compatible with many files and many data science languages, and different ways to install and use Jupyter Notebooks. In this video, we will go through the basics of getting started with Jupyter. In the lab session of this module, we can launch a notebook using the Skills Network virtual environment. Simply click on Open Tool and the environment will open Jupyter Lab. The lab will open a notebook like this one. When we start the notebook, we can change the name by clicking on File, then renaming the notebook to the preferred name. We can now start working with our new project. Let us print Hello World to show that the environment is working properly. To get an output from a code cell, you must run the cell. To run the cell, place your cursor in the cell and click on Run on the top of your screen. Then click Run Selected Cells to run the current highlighted cells. To use a shortcut, press Shift+Enter. You can also run all the cells in the notebook by clicking on Run All Cells. To add code to a new cell, click on the plus symbol. You can work with multiple files. You can do that by clicking the plus button above the folders in your local machine, then choose the file you want to open. We will open another notebook. You can also use the File option to open a new launcher or open a new notebook. When we open the new file, we can move them around based on our preference. When working with multiple notebooks for the same problem, I like to put them side by side so I can see both notebooks at the same time. Now we will assign the variable 1 to the number 1 and the variable 2 to the number 2, and we will find the result of adding 1 and 2. To delete a cell, highlight the cell and click on Edit and choose Delete Cells. To use a shortcut, press D twice on the highlighted cell. If you decide to move your cells around for better flow within the notebook, you can either move the cell up or move the cell down depending on your preference. As data scientists, communicating our results is a big and important part of our jobs. Jupyter supports presenting results directly from the notebooks. You can create Markdown to add titles and text description to help with the flow of the presentation. To do that, click on the drop-down bar by code and select Markdown. We will create line plots and convert each cell and output into a slide or a sub-slide depending on preference, and we will have a presentation. The slides functionality in Jupyter allows us to effectively deliver code, visualization, text, and outputs of executed code, as this is very important for presenting data science projects. When you are done with your notebook or notebooks, you can shut them down. This helps free up the memory that the notebook is using. To do this, click on the stop icon on the sidebar. It is normally the second icon. You can either terminate all sessions at once, or you can terminate or shut them down individually. After you shut down the notebook session, you will see no kernel at the top right of the notebook, confirming it is no longer active, and you can now close the tabs. You should now be familiar with run, delete, and insert a code cell, how to run multiple notebooks at the same time, Jupyter's capabilities for presenting a notebook using a combination of Markdown and code cells, and how to shut down your sessions after you are done. In this video, you will learn about kernels in the Jupyter environment. A notebook kernel is a computational engine that executes the code contained in a notebook file. Jupyter kernels for many other languages exist, and we will explore some of the ones that are relevant in data science. When you open a notebook document, the associated kernel is automatically launched. When the notebook is executed, the kernel performs the computation and produces the results. Depending on the environment you are using, you may need to install other notebook languages in your Jupyter environment. In the Skills Network Lab environment, a few of the languages have been pre-installed for you. The first one is the Python kernel. When you launch a notebook, pick the language you are interested in for your data science project. The Python kernel allows you to run Python cells. You can run the Python script to produce results. On the top right corner, it tells you what kind of kernel it is. In this case, it is a Python kernel. You can also run other kernels either by choosing the preferred kernel on the launch page or by clicking the top right to switch the kernel to the preferred kernel and picking the kernel from the drop-down menu. If you are running it on your local machine, you may need to manually install the languages through your command line interface. The Skills Network Virtual Jupyter environment has Apache, Julia, R, and Swift. Depending on your preference and type of project, you can use any of the languages that the Jupyter Notebook supports to execute your code. You should now be familiar with what a kernel is, how the Jupyter Notebook supports different languages, and how to switch to a different kernel. In this video, you will learn about the basic architectural design of the Jupyter ecosystem. Jupyter implements a two-process model with a kernel and a client. The client is the interface offering the user the ability to send code to a kernel. The kernel executes the code and returns the result to the client for display. The client is the browser when using a Jupyter notebook. Jupyter notebooks represent your code, metadata, contents, and outputs. When saved, it uses a .ipynb extension and a JSON structure. When you, the user, saves it, it is sent from your browser to the notebook server, which saves the notebook file on a disk as a JSON file with a .ipynb extension. The notebook server is responsible for saving and loading the notebooks. The kernel gets sent the cells of code when the user runs them. Jupyter also has an architecture of how it converts files to other formats. It uses a tool called nbconvert. For example, if we want to convert a notebook file into an HTML file, it will go through the following. The notebook is modified by a preprocessor, an exporter converts the notebook to the new file format, and a postprocessor will work on the file produced by exporting it. After conversion, when you give the URL of the HTML file, it first fetches the notebook, converts it to HTML, and displays the file to you in an HTML file. You should now be familiar with the two-process model implementation of Jupyter, how notebook servers communicate with kernels and clients, and the architectural design of how notebook files are converted to other files. Welcome to a gentle introduction to R and RStudio. This tutorial introduces you to the R programming language and its environment. The videos following will contain tutorials and hands-on practice. R is a statistical programming language. It is a powerful tool for data processing and manipulation, statistical inference, data analysis, and machine learning algorithms. Based on 2017 Stack Overflow visits, they found that R is most used by academics, healthcare, and the government. R has many functions which support importing data from different sources. For example, flat files, databases, the web, and statistical software like SPSS and Stata. R is a preferred language for some data scientists because it is easy to use the functions within R. It is also known for producing great visualizations and readily available packages to handle data analysis without the need to install any libraries. To use R, we need an environment to help run the codes. One of the most popular environments for developing and running R language source code and programs is RStudio. RStudio is an integrated development environment that helps improve and increase productivity with the R language. RStudio includes a syntax highlighting editor that supports direct code execution and where you keep a record of your work, a console for typing R commands, a workspace and history tab that shows the list of R objects you created during your R session and shows the history of all previous commands, and a plots, files, packages, and help tab for showing files in your working directory, history of plots you have created, and allow for exporting plots to PDF or image files, external R packages available on your local computer, and help on R resources, RStudio support, packages, and many more. If R is your tool of choice for data science, here are some popular libraries in the data science community. dplyr for manipulating data, stringer for manipulating strings, ggplot for visualizing data, and caret for machine learning. To get you up and learning quickly, we have provided you with an RStudio virtual environment as part of the Skills Network Labs. This virtual lab environment is designed to assist you to easily practice what you learn in the course and skip the need to create an account or download or install anything. You should now be familiar with the capabilities of R and its uses in data science, the RStudio interface for running R codes, and popular R packages for data science. With the increasing amount of data, one of our many jobs as data scientists is to produce insights using visualizations. R is a great tool for data visualization and has different packages. Some of the popular and top data visualization tools include ggplot, which is used for data visualizations such as histograms, bar charts, scatter plots, etc. It allows adding layers and components on a single visualization. Plotly is an R package which can be used to create web-based data visualizations that can be displayed or saved as individual HTML files. Lattice is a data visualization tool that is used to implement complex multivariable data sets. Lattice is a high-level data visualization library. It can handle many of the typical graphics without needing many customizations. And Leaflet is very useful in creating interactive plots. Depending on your need and data science project, most of these libraries and packages can come in handy. To install these packages in your R environment, use the install.packages and the package name command. R also has its own inbuilt functions to create plots and visualizations. It is mostly used using the plot function. For example, the function above is the simplest form of the plot function, and it returns a scatter plot of the values versus the index as shown here. You can also add lines to the function and add a title to make it easier to read and understand. Here we add a line to the plot and to add a title. We specify the title function, and we can see we have added a line and a title. We can create more beautiful visualizations using the ggplot libraries. ggplot is a data visualization package for R. It can handle complex requests, allowing for you to add layers into plots by tweaking the functions and arguments. To create a scatter plot, we will use the inbuilt dataset mtcars. We will first read ggplot library into memory by using the library function, and then call ggplot on the data frame mtcars. Specify the x-axis as miles per gallon and y-axis as weight, and then add the geomePoint function to specify to ggplot that we want a scatter plot. Otherwise, it will return an empty plot. It will produce a more beautiful and easier to read plot like this. You can also add titles and tweak the access name by using the ggtitle argument to add a title. Add the labs argument to change the names of the axis by specifying the new names we want to see. We will see an easier to read and understand graph. In our lab, we will be recreating the above graphics with ggplot and the extension library called ggalley. ggalley extends ggplot2 by adding several functions to reduce the complexity of combining geometric objects with transformed data. Please type and execute the following command in the console window to install both packages. You will not need any coding experience as the code and commands will be given to you. You are now familiar with popular data visualization packages in R: plotting with base R plot function, plotting with ggplot, and adding a title and changing the axis name using the ggtitle and labs function. In this video, you will get an overview of Git and GitHub, which are popular environments among developers and data scientists for performing version control of source code files and projects, and collaborating with others. You can't talk about Git and GitHub without a basic understanding of what version control is. A version control system allows you to keep track of changes to your documents. This makes it easy for you to recover older versions of your document if you make a mistake, and it makes collaboration with others much easier. Here is an example to illustrate how version control works. Let's say you've got a shopping list, and you want your roommates to confirm the things you need and add additional items. Without version control, you've got a big mess to clean up before you can go shopping. With version control, you know exactly what you need after everyone has contributed their ideas. Git is free and open source software distributed under the new general public license. Git is a distributed version control system, which means that users anywhere in the world can have a copy of your project on their own computer. When they've made changes, they can sync their version to a remote server to share it with you. Git isn't the only version control system out there, but the distributed aspect is one of the main reasons it's become one of the most common version control systems available. Version control systems are widely used for things involving code, but you can also version control images, documents, and any number of file types. You can use Git without a web interface by using your command line interface, but GitHub is one of the most popular web-hosted services for Git repositories. Others include GitLab, Bitbucket, and Beanstalk. There are a few basic terms that you will need to know before you can get started. The SSH protocol is a method for secure remote login from one computer to another. A repository contains your project folders that are set up for version control. A fork is a copy of a repository. A pull request is the way you request that someone reviews and approves your changes before they become final. A working directory contains the files and subdirectories on your computer that are associated with a Git repository. There are a few basic Git commands that you will always use. When starting out with a new repository, you only need create it once, either locally and then push to GitHub, or by cloning an existing repository by using the command git init. Git add moves changes from the working directory to the staging area. Git status allows you to see the state of your working directory and the staged snapshot of your changes. Git commit takes your staged snapshot of changes and commits them to the project. Git reset undoes changes that you've made to the files in your working directory. Git log enables you to browse previous changes to a project. Git branch lets you create an isolated environment within your repository to make changes. Git checkout lets you see and change existing branches. Git merge lets you put everything back together again. To learn how to use Git effectively and begin collaborating with data scientists around the world, you will need to learn the essential commands. Luckily for us, GitHub has amazing resources available to help you get started. Go to try.github.io to download the cheat sheets and run through the tutorials. In the following modules, we'll give you a crash course on setting up your local environment and getting started on a project. In the previous video, you learned about Git and GitHub. Before you continue with this video, register for a GitHub account and log in. Let us start by creating a new repository. Click plus, then click New Repository. To create a new repository, you need to provide these details. Give your new repository a name. Optionally, add a description of your repository. Choose the repository visibility, whether you want it to be public or private, and choose the option to initialize this repository with README file. Then click Create Repository. You will now be redirected to the repository you have created. The root folder of your repository is listed by default and it has just one file, readme.md. Now it's time to edit the README. You can do this in your browser. Just click the pencil to open the online editor and you can change the text of the README. To save your changes to the repository, you must commit them. After you have made your changes, scroll down to the Commit Changes section. Add a commit message and optionally add a description. Then click Commit Changes. Commit Changes is used to save your changes to the repository. Go back to the home screen by clicking the repository name link. Note that the README file is updated and verify your changes. Let's learn how to create a new file using the built-in web editor provided by GitHub, which runs in the browser. Click Add File, then click Create New File to create the new file. To create a Python file called firstpython.py, first, provide the file name. Next, add a comment that describes your code. Then, add the code. Once finished, commit the change to the repository. You can see that your file is now added to the repository, and the repository listing shows when the file was added or changed. When you need to change the file, you can edit it again. Click the file name, then click the pencil icon, make your edits, and commit the changes. You can also upload a file from your local system into the repository. From the home screen of the repository, click Add File and choose the Upload Files option. Click Choose Your Files and select the files you want to upload from your local system. The file upload process may take a short time, depending on what you are uploading. Once the file finishes uploading, click Commit Changes. The repository now reflects the files that were uploaded. In this video, you learned how to create a repository, edit files, and commit changes using the web interface. In this video, you will learn how to create and merge a branch using the GitHub web interface. A branch is a snapshot of your repository to which you can make changes. It is a copy of the master branch and can be used to develop and test changes to the workflow before merging it back to the master branch. In Git and GitHub, there is a main branch. The main branch, which is called master, is the one with deployable code and the official working version of your project. It is meant to be stable, and it is always advisable never to push any code that is not tested to the master. Many times, we want to make changes to the code and workflow in the master branch. That is when we create a copy of the master branch. Let's call it child branch. We will then create a copy of the workflow to the child branch. In the child branch, changes and experiments are done. We will build and make edits, test the changes, and when we are satisfied with the changes, we will merge it back to the master branch where we prepare the model for deployment. We can see that all of this is done outside of the main branch, and until we merge, changes will not be made to the workflow before we branched. To ensure that changes done by one member do not impede or affect the flow of work of the other members, multiple branches can be created and merged appropriately to the master after the workflow is properly tested and approved. To create branches in GitHub, let's look at this repository. There is currently one branch in the repository. I want to make some changes, but I don't want to alter the master in case something goes wrong. We will create a branch. To do that, we will click the drop-down arrow and create a new branch. Let's name it Child Branch, and then we will click Enter. The repository now has two branches, the Master and the Child branch. You can check this by selecting Child Branch in the Branch Selector drop-down list. Whatever was in the Master branch was copied to the Child branch, but we can add files to the Child branch without adding any files to the Master branch. To add a file, make sure Child Branch is selected in the Branch Selector drop-down list. Click on Create New File. In the space provided, name the file. We will name it testchild.py, and then we will add a few lines of code. We will print the statement inside Child Branch. At the bottom of the screen, we will see a section called Commit New File. Commit messages are very important as it helps to keep track of the changes that were made. It is important to add a descriptive commit message so that the other team members can understand it. Here we will add a commit message, create testchild.py. Then we will commit the new file. The file gets added to only the child branch. We can check this by going to the master branch by clicking Master from the Branch Selector menu. And here we can see that the new file is not added to the master branch. After we have created the new file, tested, and made sure that it is up to standards, we then want to merge the changes in the child branch to reflect in the master branch. To merge these changes, we will first have to create a pull request, also known as a PR. A pull request, in simple terms, is a way to notify other team members of your changes and edits and ask them for review so they can be pulled or merged into the master branch. Pull requests are the heart of collaboration on GitHub. When you open a pull request, you're proposing your changes and requesting that someone review and pull in your contribution and merge them into the target branch. Pull requests show the differences of the content from both branches. To open a pull request and see the differences between the branches, click on the Compare and Pull Request button. If you scroll down to the bottom of the screen, you will see something like this that shows you the difference between both branches. As you can see on the screen, it shows that one file has been changed and the file has 2 additions, which are the 2 lines we added to the file, and 0 deletions. We will now create the pull request. Add the title and an optional comment for the pull request. Click Create Pull Request to create the pull request. You can assign team members to review and approve pull requests. On the next page, you will see this image. If you are okay with the changes, click on Merge Pull Request and click Confirm. You will get a confirmation that the pull request has been successfully merged. You can now delete the branch if you no longer need to make any edits or add new information. Now, the child branch has completely merged with the master branch. You can check the master branch, and we can now see it contains the testchild.py file. You should now be familiar with how to create and merge branches using the web interface.
So welcome to a little introduction to Git and GitHub. It's very basic, so if you have absolutely no clue, then this is for you. Otherwise it's maybe boring. I'm just telling you how I'm using Git, and I'm able to survive in most of the cases with that knowledge. Sometimes I have to read the documentation for the more advanced stuff, but in, let's say, 80% of the cases, what I will tell you now is sufficient. So let's actually start using GitHub. It makes things a bit more easy. There's also competition to GitHub. This is GitLab. GitLab is particularly interesting because the whole system behind GitLab is open source. So this is a hosted version, but you can have the whole system on-prem and also purchase support from GitLab. Those guys are partially in Berlin, so they are pretty cool. Anyway, let's start with GitHub here. So what I will do now is create a repository. So a repository is the stuff, the location where your stuff goes in, no? Okay, so let's call it, I don't know, demo. And we can choose whether we want to create a public or a private repository. So that repository is remote, okay? That's hosted at GitHub. And let's initialize with a README and also with a, no, let's keep Git ignore for now. I will show you that later. So we create now the repository, and once this is created, it's very easy to have a copy of this repository locally. There are two options. One is cloning it via HTTPS or via SSH. So I'm always using SSH. SSH just makes things a bit more easy. The only thing you need to do is you have to add your public identity to GitHub. I can show you that later. So now the only thing we need to do is we go to an empty folder, and then we say git clone and this link. So git clone and this link. Okay, so what now happens is the contents of this is copied to my machine. Here I have to specify my password for my SSH identity, so that's something I need to explain you later. So if we now go to demo, we will see here the README file, and you see here there is contents of the README file. Okay, now let's add a file. So so you see here there's only the README and the .git folder. Please never ever touch it. Okay, so let's create another file. Let's say vi test.txt, and hello, this is a test. And now we add this to the repo. So first of all, we say git add test.txt, and now if we say now git status, then we see that this file is now in the so-called staging area. Okay, that's something in between your local folder and your local repository. So you have a local folder with the contents, you have a local repository and you have a remote repository. And you personally, you work with your local repository, and all the other guys working together with you are working also with their local repositories, and you sync all your contents with a remote repository. Okay, so now we want to commit. So we say, or let's do something else. Let's say we create a file test2, and now we say git add test2.txt. Now, interestingly, if we now say git status, those are both in the staging area. And now if we say git commit, and we say a message initial commit, that is now in our local repository on this machine. Okay, and the idea is, why you have the staging area, you can control which files go into a commit, because the, let's say, the atomic entity here in Git is the commit. So everything is built around the commit. So you can here definitely control which files are going into a single commit. And now what you want to do is you want to push the contents of your local repository to the remote repository, because if you now go to this GitHub project, you see there is no additional file. Okay, so we say now git push, and what now happens is I again have to provide a password. I don't have the key manager, the key agent running. So now you see here we have committed this local change in the local repository to the remote repository. And now you can see that you have these two files here. And if you click on that file, you see first of all the content, and also you see here which commit was responsible for adding this file. Okay. Another interesting thing is, if you are starting from scratch, you can actually also do the following. Okay, now let's delete this project. And this is a bit hard, just to make sure you don't do that accidentally. So delete this repository, and you have to say demo here. Oh no, I think you have to type the whole thingy here. So now this project is deleted. Okay, so now let's do something else. Let's create a new repository, but now let's init the repository on my machine. Let's call it demo again. We don't initialize it with a readme. So we say create repository, and if you're lucky, GitHub will show us how to do it. Yeah, here. Okay, let's actually do it ourselves. So let's get rid of the demo folder. And let's create it again. And now do what they tell us. So we create a readme, and then we say git init. So now we have it initialized, because now we have the .git folder, which you never ever should touch. And now we say git add readme, but we can also say git add dot. So it's adding everything which was in our folder, so that's only the readme.md. And then we say git commit as usual, test or whatever. And now we can't say git push now. Okay, if we say git push, it doesn't know where to push it, because actually we haven't told this local folder that it should connect to a remote repository. That we do with git add remote remote at origin, and that's the URL of our project. And then we can say git push u origin master, and that's basically it. So we have to re-enter the password for my RSA key, and if we are lucky and everything worked fine, we can now go to the project and we should see the readme file, which is the case. Okay, that's it for now. That's the first part. In the next video, I will show you how to do branches and actually also how to create pull requests. Okay, thanks for watching and see you later. welcome back to the second part of my little GitHub for Dummies series. One thing I forgot in the last video is how to sync if someone else has made a change. Okay, so let's consider this repository here. We have nothing inside, so this is actually the remote repository here on GitHub. So we will again create a little README file. We add README and we say git add, and then we say git commit blah blah, and then git push. Okay, so then we have the README file here, and now let's create a new file in the remote repository. That's something which will happen also if someone else pushes something to that repository. You will see a new file, and this is now only in the remote repository and not in my local. You see here there is only the README, not the new file. So to obtain this new file, you say just git pull, and then you see here the new file is also here. Yeah, that's basically it. And then interestingly, let's say you are, for example, working on a huge sub-project in that repository, and you don't want to interfere with the main work going on. So the main work is basically called a branch, which is master, and you can create your own branch. So you can say git branch, my branch, for example. So, and then we still, if you say git status, we still see that we are here on the master branch. Now we say git check out my branch, and now see we are switched to my branch, and now we say git status. You also see here we are on my branch. Okay, now what I do is we say here we have those two files, and then we say stuff on branch here, and we say stuff on branch.text. So git add stuff on branch, git commit blah, and git push. Yeah, we have to also create this branch remotely. So, and now we push it to a remote branch. So now we can actually see that my branch has been created here, and you see here that file stuff on branch, which is not on the master. Okay, so what we do now here is we switch back to the main branch. So that's git check out master, and then we say git merge my branch. So this has been automatically merged. So you see here we have stuff on branch also in my local folder here, but we see here it's still not in the master. Okay, that means we say git push so, and if we now refresh, we see stuff on branch. So what happened here is we have merged from the local branch repository into the local master repository, and now we push the contents of the local master repository to the remote master repository, and that way we merged the branch back into the master branch. Okay, so that's all for now here, and in the next video I will show you how to actually create pull requests and contribute to foreign repositories. Okay, thanks for watching and see you in a second. Okay, so this is the last video now on the series Git for Dummies. So I just want to show you how to fork a repository on GitHub, how to commit to the forked repository, and how to create a pull request. Okay, so let's consider you want to contribute to the very best and most important GitHub repository on the planet. This is the Coursera repository in the IBM organization, which I'm maintaining. And let's assume you have found an error in one of those software components. I mean, it's impossible that there is an error, but just consider there is an error and you want to fix it. So what we can actually do is, you can either ask me to give you commit rights to that repository, but it's better if you just create a fork of this repository and then commit to your repository, to your fork, and create a pull request. So let me show you how that works. So you see here 529 other forks already forked this repository. By the way, just give me a star if you like. I want to have 1,000 stars soon. Here you can click on fork, and then it asks you where you want to fork it into. So this is in the IBM organization, and I'm now forking it into my private account. And that means I will have a Coursera repository in my account here, and you see here even it's showing me forked from IBM Coursera. Okay, now I can change something. I can either make changes directly in here, but to make it a bit more complicated, let's actually make the changes locally. So I clone it. Oh, I shouldn't forget to show you how to add your RSA public key to the GitHub repo, but to the GitHub system, but I'll do that later. So I'm now cloning this Coursera repository, this remote repository, into my local repository, and you see here again it's in the Romeo Kinsler account, which is basically a copy of the official IBM one, and I think we have to wait a bit because it's quite huge. I should have maybe set up 2 little test repositories, but anyway, let's wait for that long. Yeah, while we are waiting, let me show you something else. So that's about the SSH keys. Okay, I'm now in my home folder, and in your home folder you have a SSH folder, and I have already created the key. So there's a private key. Never ever give it to anybody, and never ever show it the contents to anybody. And you create those, and you can set a passphrase for the keys. And I will put the commands for creating those into the description of this video. But that's the public key that you can safely give to anybody and share with anybody. So I can also do that here. So I can show you the contents. So see, that's the public key. And what I do is, if I go to the GitHub page, I have to go to, I think, the account settings. Here, SSH and GPG keys. So you see here, here you have to add the key. So you can say new SSH key, and you just paste the contents of the public key. And now I'm not doing that because I've already added it, but that's all you need to do in GitHub. And from now on you can use SSH, because only you have the corresponding private key to that public key here. Therefore you can safely authenticate against GitHub. Okay, so you also know this, and I'm hoping that in the meanwhile this other, the cloning is done. So go to Coursera and let's have a look into that repository. So we have the README, for example. Let's have a look at the README. Maybe there's something I can improve on the README. So this is the GitHub project for the following Coursera specialization. So let's put Coursera into a capital and save. Okay, as you remember, I need to say git add, and then if I say git status, the readme file is modified. Okay, I say okay, git commit, and I say now message. Now it's important, since this is a real repository, I cannot just write a crap message. Corrected little typo, and now I say git push. Okay, so now the corrected readme is in my local repository and in a remote repository, but only in my private account. Okay, if I go to this repository here, so in my private account, then if I click on readme, so first of all, you see here 21 seconds ago it has been changed. You see here the commit message, corrected little typo, and if I click on the readme, you see here the C is now capital case. Okay, now I want to get this change back into the official repository IBM/Coursera, and you see here there's a contributor, so she also committed some stuff via pull request into the main repository. Okay, so it's straightforward. You can create a pull request easily here on that button, and then the difference between my repository and the official repository is just used, and you see here the only difference is here the little typo correction. I say create pull request. Okay, so that's something I'm doing as a potential contributor. I say create pull request. Okay, so now I myself, as I'm administrator of the IBM repository, I will get the email, and you see here I'm already forwarded. So let's consider I'm not Romeo, I'm somebody else, the administrator of the repository, and here I see there's a pull request coming in, and I will review it. So I see, okay, cool, someone fixed the little typo in my repository. That's something I can definitely accept. So I say merge pull request, confirm merge, and usually what I then say is merged. Thanks a lot or so. Okay, so you have to be polite to your contributors. Now here I'm in the Coursera repository, and if we now click on readme, you see here there's a capital case, and that's basically how it works. No, here you see the commit and the commit message, and that's basically all. So I hope this helped you a bit. So with that knowledge, you will survive around 80% of your Git and GitHub problems and work. If you have specific questions, feel free to ask me in the discussion forum or in the comments below the video. And thanks for watching, and have a nice day. Bye. Thank you very much.
Every business wants to work smarter, and to do that, you need to tap into your company's greatest resource, your data. But extracting the full value out of your data isn't always an easy process. First, you end up juggling an incredibly large and complex collection of tools that are used for finding and cleaning data, analyzing and generating visualizations of that data, and using the data to build and deploy machine learning models. And to make matters worse, These tools are often a time drain to individually manage and can be difficult to integrate into your system, which can really slow down the workflow. But not anymore. Using Watson Studio, you can simplify your data projects with a streamlined process that allows you to extract value and insights from your data to help your business get smarter, faster. It delivers an easy-to-use collaborative data science and machine learning environment for building and training models, preparing and analyzing data, and sharing insights, all in one place. Watson Studio's easy-to-create visualizations and drag-and-drop code put the power of database decision-making into the hands of any member of your organization with no need for IT assistance. And if you need access to open-source tools, the environment offers some of the most popular and powerful ones available. Watson Studio's single environment also creates a workflow that's incredibly efficient, so data scientists can share assets and work to solve problems within the system, rather than starting from scratch every time a new issue arises. And developers can use that efficiency to quickly dive into building machine learning and deep learning algorithms. In fact, in the area of deep learning, Watson Studio supports some of the most popular frameworks and can deploy that deep learning onto the latest GPUs to help accelerate modeling by making it easier to use. The environment's built-in neural network modeler also helps you build models with a simplified graphical interface. Even if you don't have the dedicated resources to build a model from scratch, Watson Studio can help you get started with modeling templates for areas such as visual recognition, language classification, and other tools from IBM Watson services. Because Watson Studio is seamlessly integrated with the IBM Watson Knowledge Catalog, an intelligent asset discovery tool, you can transform data and models into trusted enterprise resources and collaborate with confidence, without compromising compliance, security, or access control.
Watson Studio provides many benefits for organizations, helping to infuse AI into the business and drive innovation. You can train Watson Studio with embedded AI services, including Watson Visual Recognition. You can customize your models and deploy them as APIs or Core ML by using open source tools like Jupyter, Notebooks, Anaconda, and RStudio. Watson Studio supports most popular code libraries, as well as no-code visual modeling with Neural Network Modeler, for designing neural architectures using the most popular deep learning frameworks. In Watson Studio, you can interactively discover, cleanse, and transform your data using Data Refinery. It helps you understand the quality and distribution of your data with built-in charts and statistics, and provides visualized results through interactive dashboards. Watson Studio includes an intuitive drag-and-drop interface that enables a non-programmer to speed up the model building process by visually selecting, configuring, designing, and auto-coding neural networks. From development and training to production and evaluation, Watson Studio tracks your models over time to ensure you have the best performance for any given task, using the best solutions across the entire lifecycle of your machine learning models.
Watson Studio is an integrated platform of tools, services, and data that helps companies accelerate their shift to become data-driven organizations. You can start with a free account to explore its capabilities. Data science is a team sport. We have different types of people interested in the insights that data science can provide. This includes business analysts, data engineers, data stewards, data scientists, and developers. Data needs to be located and cleansed. Models have to be created, tested, monitored, and updated. All this requires teamwork. For this reason, Watson Studio was built as a collaborative platform, a community of like-minded people. There is a lot to cover in this introduction, and we will only scratch the surface. You can find more information on the digital technical engagement site at ibm.com/demos. Once you are logged in, you may see the Get Started welcome screen. You can minimize the screen by clicking on the Get Started button in the upper right. One important item that is easy to miss is the hamburger button in the upper left. It gives you direct access to projects, catalogs, and services, among other things. The gallery is particularly interesting. It is a collection of assets including tutorials, notebooks, datasets, articles, and papers from multiple sources. New assets are constantly added. Assets can be searched using filters for type, language, technology, topics, and so on. The results can be sorted by features or by date. Manage gives you quick access to specific areas to manage. Finally, we have integrated support and documentation in the Watson environment. As mentioned earlier, the project is the center of the collaboration. It is very simple to create a project. You click Create a Project in the Welcome screen or New Project and either create an empty project or one from an existing one. Then you give it a name, possibly add a description, and you are ready to go. At the project level, we also have a menu of options. It starts with the overview where you can see basic information on the project. This tab also includes a README section where you can give more details on what the project is about. The next one is Assets, where you can see the data assets, models, notebooks, and other assets that are part of the project. You can go to add specific assets using the Add to Project drop-down menu at the top of the screen. We won't go into all of those menu items, but one important one to know is Connection. This allows you to access data that comes from outside Watson Studio. As you can see, it includes a lot of data services from IBM, but also quite a few from third parties such as Amazon and Microsoft. Going back to our project, I'd like to point out the Environment section. One important tool for data exploration, data manipulation, and model creation is the notebook. Depending on the amount of work that needs to be done, we have a choice of resource allocation. We can also tailor the environment to include additional libraries, so we have a complete environment from the start. I want to point out two more selections from the top menu, Access Control and Settings. The Access Control allows you to control collaborators and their permissions and more. In the Settings section, you can, among other things, add services. For example, you click on the Add Service drop-down menu, select Watson, and add a machine learning service. You have the choice to add an existing service you may have created earlier in another project, or create a new one. Note that most services include a light, free version. This means that you can experiment with all sorts of capabilities for free.
This video shows you how to try out IBM Watson for free. IBM Watson gives you access to IBM Watson Studio, IBM Watson Knowledge Catalog, the Data Refinery, Machine and Deep Learning, Visual Recognition Models, Dashboards, and Streams Flows. At dataplatform.cloud.ibm.com, you can sign up for a free trial. When you sign up for an IBM Watson account, you are automatically signed up for a free IBM Cloud account. Here you see the Watson applications that will be provisioned, IBM Watson Studio and IBM Watson Knowledge Catalog. If you already have an IBM Cloud account, then use your IBM ID to sign up for IBM Watson. Otherwise, type your email address, which will be used to create an IBM Cloud account for you. On the next screen, you are redirected to the IBM Cloud registration page, where you need to provide the typical basic information for an account. Then click Create Account. Now check your email and confirm your account. Now that you've registered for IBM Cloud, you can use those same credentials to sign in. Next, you'll see the process Create the IBM Watson user account using your IBM Cloud credentials. And finally, you'll see that your account was successfully created. This IBM account has only one associated IBM Cloud account and one resource group. If you have more than one associated account, or one account with multiple resource groups, then during the Watson Studio account setup, you'll see this screen giving you the option to select an account and resource group to use. IBM Cloud uses resource groups as a way for you to organize your account resources in customizable groupings so that you can quickly assign users access to more than one resource at a time. View the settings to verify the applications and services that are provisioned. Now you're ready to start working in IBM Watson. This video covers the basics for working with Jupyter Notebooks in Watson Studio. Start in a Watson Studio project and add to the project a notebook. Just provide a name and a description and create the notebook. Let's first load a file so you have some data to work with. From the File slide-out panel, browse to select the file. After the file is added to the project, it's available to work with in this notebook. Just click Insert to Code and insert a Pandas data frame. Before running the notebook, it's a best practice to insert a cell at the top to describe what the notebook does. Change the cell type to Markdown so this cell will not be treated as code, and then add the description. Now you're ready to run the notebook. The inserted code loads the dataset into a data frame using your credentials for your Cloud Object Storage instance, and then displays the first 5 rows of the dataset. Before returning to the project, save the notebook. On the Assets tab, you'll find the notebook. If you open the notebook, it will be in read-only mode. But you can edit the notebook and make changes. For example, you can access the Info panel and change the name of the notebook. And on the Environment tab, you could change the environment used to run the notebook, as well as stop or restart the runtime environment. If you'd like to share a read-only version of the notebook, you can do that from here. You can select how much of the content you'd like to share and how you want to share the notebook, either through a link or social media. If you'd like to schedule the notebook to run at a different time, you can create a job. Just provide a name for the job and select the scheduling options, like specifying a date for the job to run and whether you'd like the job run to repeat. After you create and run the job, you can see the status on the Jobs tab in the project. This video shows you how to create a Jupyter notebook. Let's start by adding a data asset to the project. You can either browse to select files or drag files into the panel. Great! Now the data file is uploaded to object storage and available as a data asset in this project. Next, create a notebook. Provide a name and a description, and then select the runtime to use when running this notebook. Here you see the environments you can use. You'll learn more about environments later. So for now, just select the default Spark Python environment and verify the language and Spark version. When you're ready, create the notebook. Now wait while the runtime environment is instantiated. Once the environment is ready, in the notebook, access the data sources and locate the file. Click Insert to Code and choose how you want to insert the data. The choices in this drop-down box are dependent upon the language used in this notebook and the file type. Notice that the inserted code includes the credentials you'll need to read the data file from the object storage instance. When you run the code, the first 5 rows display. Now let's take a closer look at environments. On the Environments tab, you can define the hardware size and software configuration for the runtime associated with Watson Studio tools such as notebooks. You can see that there is one active environment runtime, namely the runtime being used by the notebook you just created. And here are the other default environments. You can view any of the default environments to see a summary of the configuration. You can also create a new environment definition. First, provide a name and a description. If you select Spark for the type, you'll see some additional configuration options. In this case, just accept the defaults and choose Scala for the software version. When you're ready, create the new environment. The environment is ready for you to use with a notebook. To switch a notebook to use a different environment, you need to first stop the kernel. Then you can change the environment and select the custom environment you just created and associate that with the notebook. Now open the notebook in edit mode and wait for the new environment to be instantiated. Since this notebook was last saved using a different kernel, you need to set the new kernel. Let's delete the existing cell, locate the source data file, and insert a Spark session data frame. When you run the code, the first 5 rows display. Now you're ready to explore the community and find sample notebooks and datasets to get started analyzing data. This video shows you how to connect your IBM Watson Studio account with your GitHub account. In Watson Studio, navigate to your profile settings. On the Integrations tab, visit the link to generate a GitHub Personal Access Token. Provide a descriptive name for the token and select the repo scope. Then generate the token. Copy the token, return to the GitHub integration settings, and paste the token. The token is validated when you save it to your profile settings. Now navigate to your projects. You enable GitHub integration at the project level on the Settings tab. Simply scroll to the bottom and paste the existing GitHub repository URL. Once the URL is validated, click Connect. Now go to the Assets tab and open the notebook you want to publish. Notice that this notebook has the credentials replaced with X's. It's a best practice to remove or replace credentials before publishing to GitHub. So this notebook is ready for publishing. You can provide the target path along with a commit message. You also have the option to publish content without hidden code, which means that any cells in the notebook that begin with the hidden cell comment will not be published. When you're ready, click Publish. The message tells you that the notebook was published successfully and provides links to the notebook, the repository, and the commit. Let's take a look at the commit. So there's the commit, and you can navigate to the repository to see the published notebook. Lastly, you can publish as a gist. Gists are another way to share your work on GitHub. Every gist is a Git repository, so it can be forked and cloned. There are 2 types of gists, public and secret. If you start out with a secret gist, you can convert it to a public gist later. And again, you have the option to remove hidden cells. So that's the basics of Watson Studio's GitHub integration.